Hello everyone and welcome to another 3D Buzz Math VTM. My name is Rob Rolnick, known on 3dbuzz.com simply as Demondo, and with me tonight we've got the brilliant
Logan Frank. I will be joining Rob tonight as we take a look at Math VTM number 4.
Excellent. So, we'll just get started.
Sounds good.
So here are some solutions from Math VTM number 3, in which you guys learnt about Gaussian elimination, and also these are also the solutions to Math VTM number 2, where we talked about systems of linear equations and how to solve using algebra. So just pause the VTM here, check your previous answers, make sure they all match up, and if you have any questions, post them on the site to see how these answers were acquired. In this lesson, now that you have the answers to the previous lesson, we're going to move on to a bit of geometry. We're going to be talking about lines and angles and how to know when lines intersect and stuff like that. So let's move on. Geometry. Well, geometry comes from two root Greek words, ge meaning earth and metry meaning measure. Just a bit of, etymology for you guys. In any case, geometry deals with the study of shapes, angles, and measurements. In this lesson, we're going to be talking mostly about angles and line measurements. Although we will not be doing any, formal proofs and constructions are done with a compass and straight edge. A compass is used for drawing, angles. Well, not really measuring angles, but drawing arcs and so forth. Whereas a straight edge is essentially a ruler without any markings. So you don't know how long something is, but you can draw straight lines. Okay, so, line and line segments. A line extends infinitely far in both directions. So you'll see that I'll just grab the pen tool. The felt tip pen tool, and you'll see that there's a little arrow at the end of each side. That basically means that although there's a certain length that you can measure that's drawn, it doesn't end there, it just keeps going. So it would be as though the line kind of just keeps on going. Is that clear?
Yeah, I mean, makes perfect sense, and obviously you have a finite amount of space to work with, like if you're drawing something out on paper. So if you need to represent a line, then that's how you do it, just to indicate that it is in fact a line and both ends extend infinitely. Exactly.
Whereas a ray, sometimes referred to as a half line, has one fixed point, you'll see the little dot there, and the other end extends infinitely far. For a ray, you'd say the two endpoints, A, B, with a little arrow over it to show that it goes infinitely far in B. A line, you basically would just say A, line A.
Yeah, it's just line
A. Okay, so line segments. A line segment essentially has two fixed ends. So it would be line segment AB. And you'll see here that there's no arrows on top of that little line on top to show that it's fixed. Slope of a line. A slope of a line is basically the measurement of how much a line increases in y versus how far it goes in x. It's a ratio. It can be written as delta y divided by delta x, or some people just prefer to do it logically and say the amount of rising it does over the amount of running in the x direction it does.
Right, good old rise over run.
Some people would make a stupid math joke saying, hey, the r's cancel and you have i's over un, but that's just a stupid math joke with variables.
Never heard that one, but cool.
In any case, in this example here, you'll see it goes up every 2 units. For every 3 units it goes in x, because it has a constant slope. So therefore, the change in y is 2, and the change in x is 3. For those of you who are unfamiliar with the delta sign, what delta, little triangle symbol, x means is you take the final point in x, so x final, and you subtract from it the initial point in x, x initial. So, for example, although we're saying only lengths here, if we knew that this point here, right here, was, let's say, 2 on the grid, on a grid that's invisible right now, and this point here was 5 on the grid, that's invisible, delta x would be 5 minus 2, which equals good old 3.
I got you. So delta x is just a way of representing, I guess you could say or a line segment.
Right, it's a way of measuring a change. Delta meaning change.
I got you. Okay, I see.
Okay, so graphing. Now that we know...
Actually, if you don't mind, may I ask a quick question about that? In that case, x would have been a line segment because you have to have a known start and end point.
Well,
or is
the
it?
distance that we're moving in x, you could say, is a line segment. But x,
It's not really a line though because it's only x, whereas a line can.
Well, x, if as we move on, we're going to show how to graph things using a Cartesian plane. And you'll see that x is an axis, which basically means it's kind of like a horizontal line that goes infinitely far in both directions. So here we're just measuring the change in x, delta x. You can't measure x on a line because x goes infinitely far. There's no fixed ends. But you can measure in a certain region how much x changes. So what you're measuring is, in a certain region, how much y changes divided by how much x changes.
And therefore, delta x itself would be the two places where you're measuring x. And
it would be
you
take
them.
two fixed endpoints, and you say how far you're moving in x in that area, and using that you find the two y points. So like here you draw like that, and up here, and then you can find out how much y moves in that same region. And that's how you measure a slope.
I gotcha.
Okay. Okay, so graphing. When graphing lines in a 2D space, so two-dimensional space, like a piece of paper that's flat, no height, a Cartesian plane, aka Euclidean plane, is often used. There are other methods of graphing things. You could use, let's say, polar coordinates, which we won't be talking about. It's outside the scope of this lesson. So I'm just saying that we'll be using the Cartesian plane. It's often used because it's really nice to and easy to draw lines using a Cartesian plane. Whereas if you did it using other methods, it might be a little more complicated. This is a pair of axes. The Cartesian plane is a pair of axes, one in the x direction, horizontal, and one in the y direction, vertical. That's what I was just saying. So x would look something like that. Imagine I can draw straight. Y would look something like that. And those are just axes, meaning like where the 2 points of the two axes intersect, you'd call the origin, and the axes are essentially where if you're at the origin, you haven't moved any in x and any in y. It's kind of like the center point of your grid. Each axis has a fixed scale, but the x and y scale do not need to have the same one. So we'll show that in the next slide, how even though you're moving a certain distance in x and a certain distance in y, it doesn't necessarily have to be the same amount, even if you measure it to be the same amount.
For convenience sake, in a certain calculation, if you knew you were going to have a wide range in y, but only a very small range in x, you can actually adjust the scales independently to more easily visualize what you're looking at. Like, what if y had changes from 0 to 1,000, and x only had changes from, 0 to 1?
Right. If you tried to graph that normally on a piece of paper, you need really, really tall paper, long paper.
And you'd be looking at tiny little grid units.
Right. So to make it easier, you might make x increase by, let's say, 0.1, because it only goes from 0 and 1, so you'd have 10 increments in x, and y increments by 100, so you'd also have 10 increments in y.
And then you'd have a nice grid that would evenly fit and be easier to visualize.
Exactly. By moving a fixed distance along x and y, you can reach any point in space. Such a point is represented as x comma y. What this means is, let's say I moved 3 units along x and I ended up here, and 2 units along y and I ended up here. Then I'd say that xy equals 3, 2. Pretty simple. Each quarter of the graph is called a quadrant. The upper right is quadrant 1, the upper left is quadrant 2, bottom left is quadrant 3, and bottom right is quadrant 4. So if you think about it, you're moving counterclockwise. You start here, and you move counterclockwise around to number the quadrants.
Simple enough.
Often you wouldn't number them 1, 2, 3, 4 using Arabic numbers, you'd use Roman numerals. But that's just convention. Okay, so here we're going to talk about how to actually calculate points in space. So what we're going to need is a value for each increment in x. Logan, do you have a value you'd like to use?
For x, we could use maybe 2.
2 is good. So 1 increment in x is 2. And how much would 1 increment in y be?
Let's keep this simple for now. Let's just say it's 1.
Okay. So each increment in y is 1. Each increment in x is 2. So 2, then this would be 4, etc. 1, then here would be 2, etc. So in quadrant 1, you're moving in the positive x direction by convention. And in the upper area, you're in the positive y direction by convention. So
and that is, of
y.
course, represented by the arrows you have representing the x and y axis. Notice the arrowheads facing to the right on the x-axis, indicating that you're going positive. And then the same arrow in the y-axis indicating that as positive y.
Right. It's a convention. You could make it the opposite if you wanted, negative x. But this is just how you generally
some
see
reason
it.
for visualizing. But yes, if you're just following convention, just plotting a point in space, then you'd probably use this as your starting point at least.
Exactly. So, this blue point here is 2, 4, 6 units in x, and 1, 2 units in y. So it would be 6, comma 2. What about this point in y, Logan?
Well, that
in quadrant 2, I mean.
In quadrant 2, that would be negative 2x.
Right.
And positive 2y.
Exactly. So following this convention, in quadrant 3, we'd have a point that's negative 2, negative 4, negative 6 in x, and negative 1 in y. And finally, in quadrant 4, you have a point that's positive 4 in x and negative 2 in y. So, it's important to realize that in certain quadrants you might have both values negative, such as quadrant 3, one value negative, such as quadrants 2 and 4, or both values positive, such as in quadrant 1. So I'm just going to jump to Photoshop for a second to illustrate one other thing. Let's say we had our axes. So here's our y-axis, and we had an x-axis. Imagine they're perfectly straight and so on.
Of course.
Let's say our x values started at 1,000 and went up to 2,000. And, well, I'm not going to care about y for this example. So
you're saying each line or each segment on the x-axis represents 1,000?
No, I'm saying that the range in x is from 1,000 to 2,000 of our values.
Okay.
You might not want to have a big empty area at the beginning. It would just of your paper.
I see. You're saying you're starting off where the origin x, I guess, is starting at 1,000.
Right. The first point we have in x, which would be, let's say, here, is 1,000.
Okay.
So what we might do is you can show a little broken sign there, the little squiggle, and then say, here is 1,000, and then you'd basically just say what the next value is, so I'll say 1,250, to show how the increments are working.
Okay, so in that case, the increments are in 250.
Right. The increments are in 250, but the first value is at 1,000.
So just showing, if you wanted to have your value start off, that's what you do, is you simply mark that off with the squiggle symbol, just to show that you have started off at a value other than 0, or other than the origin. Exactly.
You're basically saying that from the origin, which is at the 00 mark, to 100, it's a straight jump. You don't really put anything there. And then at 1,000, our values are starting, so we'll put it there. We'll put a 1,000 mark. And then from 1,000, it'll be 1,250, 1,500, etc.
So it basically facilitates an offset.
Exactly. It's basically exactly that, an offset. And then using that, you can still find every point you need without having a big white spot on your grid.
Right. Yeah, that could be very helpful.
It is. Graphing lines. When plotting lines on a Cartesian plane, it is important to realize that there is a linear relationship between x and y. So, no matter what, if there's a change in x, there's a corresponding change in y. This means that for any shift you make in x, y has a proportional shift. Think back to the slope, which basically said there was a ratio between x and y when you're talking about slope. As a result, there are many ways of expressing a line, such as the general form. The general form is important because it lets you express any line in the general form. Horizontal lines, vertical lines, sloped lines, or lines that go through the origin. They can all be expressed using the general form. The intercept form, as expressed here, is really nice because it clearly tells you the point in x and the point in y where you're hitting the axes. So, x divided by a plus y divided by b equals 1. Let's say a was 3. That means if a was 3, a equals 3, that means your x-intercept is at 3. So you're hitting the axes at 3, 0. Because the x-intercept means you're 0 in y, whereas the y-intercept means you're 0 in x. And similarly for b, if that had a value, let's say 5, your y-intercept would be 0, 5.
Right, because, that makes sense. You're intercepting the y-axis, and therefore crossing over that would be, or allow you to measure it.
Exactly. The point slope form lets you draw a line if you know a point and the slope of the line. So, for instance, x1 comma y1 would be a point in space. It can be anything. x1 comma y1. And if you knew this point and the slope of the line, then you can draw any line in space. Don't worry if this is very confusing right now. In the coming slides, we'll be showing you examples of how to graph using each of these methods.
Okay.
And the slope-intercept form lets you draw a line if you only know the y-intercept and the slope. What I'm hoping you guys gather from all of this is that to draw a line, you need a point, so like the y-intercept being a point, and the slope of a line. Or you can draw a line using 2 points by just connecting them. Like I said, there's other ways, such as the 2-point method of drawing a line. So, we'll move on. The general form. As you can see from the general form, we're drawing a vertical line. The general form is unique in that it is the only form that I've shown you that lets you draw a vertical line.
Okay.
So let's say you wanted to figure out how to actually tell that this is the vertical line you get from this equation. What you can do is, using some algebra that we talked about earlier, you know that 2x equals 6. Therefore, x equals 3. And assuming the scale on our graph is 1, and the y-scale doesn't really matter, but I'll put a 1 anyway, then here is 3 in x. 1, 2, and then the line would be in the 3. But what do we know about y? Well, y can be anything. If y was 5, that wouldn't change anything in our equation. If y was 17,000, that wouldn't change anything in our equation.
Y isn't in the equation.
Exactly. So, when x has to equal 3, but y can be anything. Therefore, a vertical line where an x equals 3 would cover all these.
A vertical line is the only thing that represents points generated using that equation.
The
equation. Right.
Perfect. So, now move on to the intercept form. The intercept form is very nice so long as your line isn't passing through the origin. You cannot use the intercept form when your line is passing through the origin, simply because x divided by 0 plus y divided by 0 has a division by 0. In fact, it has 2 of them. So if your line is not passing through the origin, meaning it's not passing through this point right here that I just circled, you can use the intercept form. So x divided by 3 plus y divided by 2 equals 1. Well, when y is 2, let's say, and x is 0, we'd have 0 divided by 3 plus 2 divided by 2, right? Because that's the point of the y-intercept.
Right.
So 0 divided by 3 is 0. You can just cross that out. 2 divided by 2 equals 1. So we just proved that this point is good. And then if you were using, let's say, the x-intercept, when x is 3 and y is 0, you'd have 3 divided by 3, which is 1, plus 0 divided by 2, which is 0, equals 1. So 1 plus 0 equals 1.
Right. And then it works out.
Exactly. And if you just draw a line connecting these 2 points, you'd see that all these other points also satisfy the equation. All the other points in the line.
Very nice.
It's important to realize that you can't express every single point in a line by saying, like, here are the points that the line covers and listing them. Because there are infinitely many points. There's like a point here and a point here and so on. Like points.
Right. I mean, the only thing that limits us is the accuracy with which we can measure. But I mean, that's not a finite limit.
Right. Exactly. You can't say that these are the points that meet satisfy the line. You can say,
yeah, there's infinitely many. There's an infinite number of points along the line.
Exactly. But you can say, by drawing a line, that say anything that this line crosses satisfies the line.
Right.
So essentially, anything that this line hits, like this point right here, would satisfy the equation. But you can't just say these points satisfy the equation and list all of them. You could say a couple of them satisfy, but so on. Anyway, the point-slope form. The point-slope form is especially useful in calculus when you're dealing a lot with slopes. We're not going to be exactly talking about the calculus uses of it in this lesson, but just keep that in mind for when you take calculus in school. In any case, if you remember the form of the line, it was y minus y1 equals m being the common variable used for a slope, but again, it can be any variable, doesn't really matter, and then x minus x1. So there we go. So in this example, y1, it says plus 1. So if it's minus y1 and we end up with plus 1, that would mean that our y value is negative 1. And I'll show that. 1 minus negative 1 equals positive 1. So therefore, this 1 right here means our negative y1 is negative 1. So we'll just write that point down. We know our y1 is negative 1.
Okay.
And negative x1 is 1 because you have still that negative sign. So 1 comma negative 1 is our point, which is right here. Right here is that point. 1 comma negative 1. And then we know the slope. We know that it increases 2 in y for every 1 it increases in x. So here would be a point. Here would be a point. Or similarly, it will decrease 2 in y.
So that could make it very easy if you want to find additional points. Once you know a point and the slope, then it becomes easier to find the points before and after that.
Exactly. And in calculus, you very frequently know a point and know a slope.
And then that's why
and therefore
so
you'd use this form because it's so valuable, like Logan just said. Okay, the slope-intercept form. The slope-intercept form is very, very nice for expressing any line except for vertical lines. You cannot express a vertical line using the slope-intercept form, simply because you're dealing with a slope. Because if you recall, the slope-intercept form is y equals m being the slope, x plus b. A vertical line would have a slope that's approaching infinity. If you can see that, I'll show that in a second. But first I'm just going to just explain that, just know that you can't express a vertical line using this form. However, in our example, our slope is 1. You'll see that it's 1x minus 3. So the y-intercept is that b value. So 0, comma, negative 3. And our slope is 1. So negative 3 in y and 0 in x gives this point. And then you're increasing 1 in x for every 1 in y. And now I'm just going to backtrack for a sec and explain the whole slope approaching infinity. If you had a line like this, you'll see that it increases more in y than it does in x than our previous line. The line that was originally drawn on the slide. I'll just change pen colors. So, in color, we'll change it to blue. And then, if I had another line, say a line like this, it's increasing even more in y for an increase in x than the other red line. Either red line, actually. Now, if I jump to green ink, and I draw a vertical line, assume this is perfectly vertical, then you'll see that it's increasing 0 in x for every increase in y. That means delta y divided by delta x would have a division by 0. Because delta y, let's say, is anything we want. We'll say 3. But it can be any number. And delta x isn't increasing. It's vertical. There's no change in x.
And that's why this doesn't work, is because to try to plot a point would result in division by 0.
Right. And as we explained in a previous lesson, as you divide by smaller and smaller numbers, your value gets bigger and bigger. So you're approaching infinity with a slope, but you can't have a slope of infinity. That doesn't make any sense.
Right, because, I mean, that's exactly what it would require. It would require that you be able to represent infinity if you were to represent the vertical line.
Exactly, which is why the slope-intercept form is really nice. You know the y-intercept, and you know the slope, so it's, like Logan said before, it's easy to find previous and subsequent points, and therefore it's a really nice form, so long as you're not dealing with vertical lines. In which case, I recommend the general form. And then, two-line interception. When trying to determine whether two lines in 2D space intercept, one must be aware of three possibilities. If the lines have different slopes, then they will intercept at a single point. Parallel lines, namely lines with the same slope, will either never intercept or lay on top of each other. We'll show this in future slides. If you want your lines to be perpendicular, meaning they intersect at right angles, so I'll just switch back to the red ink because I don't really like the color green. If you wanted your lines to intersect like at a right angle, say like that, or say imagine this was a right angle, say like that.
Same idea.
Yeah, exactly. I just rotated. Then the slopes need to be negative reciprocals of one another. So if one slope was 3, then the other slope would need to be, it would become, for the perpendicular line, negative the reciprocal 1/3. Because you can imagine 3 being 3 divided by 1.
Right.
In any case, this also explains the vertical line problem. As you can imagine, a horizontal line would have an increase in y of 0 for any increase in x, because it's horizontal. It would look like something like that. So delta y divided by delta x, delta y isn't changing, y does not change, so 0 divided by any change in x. Doesn't really matter, we'll say 1. And that's 0. 0, not 1. If you take the negative reciprocal of that, you'd be dividing by 0, which again leads to the whole problem of the infinity problem. In any case, that's how you do perpendicular lines, if you want them to intercept at right angles. So, in this slide, you can see that if two lines have a different slope, and I picked 2 slopes, it can really be any 2 slopes. They'll have to intercept. So, as you can see, in this case, they intercept here, but they can really intercept anywhere, depending on the slopes and the lines themselves.
Right, of course, because that means that with their slopes changing, that means depending on the direction you're going, they're either getting closer or farther apart. And if you continue in the direction where they get closer, eventually you're going to hit a point where they intercept.
Right, and past that point, they'll be getting further apart. Parallel lines have the same slope. So, for instance, here, this line, if you look, is decreasing 1, 2, 3 units in y for every 1 unit it increases in x. Similarly, this line is doing the same thing, decreasing 3 in y for every 1 unit it increases in x. So the slope of each of these lines is negative 3 divided by 1. And that's the slope of both of them. But because their slopes are the same, they're always equally far apart. One common mistake that people make when measuring how far 2 lines are apart is they'll just go, they're this far apart. That's not right.
It's really hard to tell, though, because, I mean, you're getting into a case where you're not dealing with actual points. You haven't even really plotted points. It's not... And it's also not taking into account the axis scale. Right.
I'm just saying that if you had a ruler, you'd measure that far, knowing the size of the axes, the increments in the axis. What you have to do when measuring the distance between 2 lines is take the perpendicular distance between them. So imagine this is perpendicular and this is perpendicular.
Basically what you're saying is to calculate the distance between 2 lines, you have to take the slope into account. You can't just measure along an axis. You have to go perpendicular between the lines.
And the easiest way to think about this, in my mind, is to think of our room. I'm going to draw a box, and imagine this is imagine these. Okay, so first imagine these 2 parts are parallel, and these 2 are parallel. So it's a top-down shot of a room. If you were taking the distance between these 2 lines that are going in the vertical direction, you need to take a perpendicular distance. That's the shortest distance when you're walking across the room, is to go perpendicularly to a wall. If you were measuring differently, say you were measuring like this, then you're not taking the shortest distance between 2 lines.
I see.
And right now you might be thinking, well, that's kind of obvious. The sides are all parallel. It's a square, essentially. Where's the challenge there? Well, imagine if you just rotated your view a little, and then suddenly these 2 lines would come up. If you moved your box to look like something like that, then you basically have this setup with these lines down here.
Right, and now you need to know the actual slope of those lines.
Exactly. And that's basically what I'm trying to get at. Okay. Moving on.
The correct and incorrect ways of measuring the distance between 2 lines.
Right. We're not going to be talking about how to actually calculate this distance. But if you wanted to, a nice way to do it is you take one of the parallel lines have the same slope. You find the perpendicular slope. which is very easy to do. In this case, it would be 3 equals 3. You simply draw any line that has a slope of 3 and calculate both points of interception, where it intercepts with the red line and the blue line.
That makes sense.
And then if you calculate the distance between those points, you suddenly have
the distance between those two lines.
Exactly. Okay, so parallel lines part 2. When parallel lines have the same slope, which essentially is the definition of parallel lines, and they cover the exact same points, they're known as coincident lines. So you'll see here that the red line is directly on top of the blue line, which basically means every single point is in common between these two lines. They don't have a single point of interception, but rather every single point is the same in the two lines, because they're essentially the same line.
Right, so it would basically be, if you were trying to plot points using either of those lines, the same points would work the same in the same equations. You'd always end up with the same point if you tried to plot using those lines.
Right, and you might be thinking, well, that's kind of obvious if lines are coincident. But let's say you had lines using two different equations. Let's say you had the intercept form and the general form. You might not immediately see that the lines are coincident until you plot them or convert between the forms. Okay, so moving on. Angles. Angles are the amount of rotation between the point where two lines intersect. So essentially you have two lines that intersect, say these two lines, and you want the angle here. Then you're measuring essentially the amount of rotation between the two lines.
So basically measuring the difference between the slopes.
Yeah. So acute angles have less than 90 degrees between them. Right angles have exactly 90 degrees. Often when you see a right angle, you'll see this little box here. That lets you know that it's a right angle. The reason you draw the box is because let's say you had an angle that was 89 degrees. It might look right angled, but you don't know until you measure it.
That's just an indicator to make it clear that you intend this to be a 90 degree angle, and then your 89 degree angle would not have that, of course.
Exactly. And even though they might look the same, you'd know by that little notation that they're not. Obtuse angles are between 90 and 180 degrees, so they're bigger than a right angle. Straight angles are exactly 180 degrees, so it's essentially a line. Reflex angles are greater than 180 degrees, so, 180, 275, so on. And full angles are exactly 360 degrees, so an entire rotation, because there's 360 degrees in a complete rotation.
So if you're measuring the angle of two coincident lines, you could either, depending on which way you're measuring, it could either be 0 degrees or it could be 360 degrees, a full angle.
Between coincident lines? So yeah, you can, depending on exactly what you're measuring, you might end up getting 180 also, depending on how you're measuring.
Oh, yeah, I can see that.
But you might get 0 or 360. And Logan brings up a 0, 360, or 180, depending on how you're measuring. But based on the drawing, it should be pretty clear that the lines are coincident. It's important to realize, though, that let's say you had a rotation of 365. That's the exact same rotation as just 5, because you did a complete rotation and then 5 more.
So generally that would be represented as 5 degrees, not 365.
Right, exactly. You can think of it, a nice way to think of angles is like a clock. Old-fashioned clock with a 12 would be up here, and the 6 would be down here, and so on. If 13 hours pass, the hand on the clock will be the same as if only 1 hour passed.
Right. Okay, I can see that.
Okay, so we'll just move on. Terminology. Complementary angles are two angles that add up to 90 degrees. So let's say we wanted to express this angle here, here that I just coded in red ink, that angle. You could say something like angle A, B, D, which basically means you start at A, you go to B, and then you go up to D, and the angle that takes place at B when doing that.
Okay.
And then if you wanted the other angle, let's say DBC plus angle DBC, well, those two would equal 90 degrees. It's also important to note that if you go ABD, you'll get the same angle as if you go DBA, if you go in the opposite direction.
Okay. So you're saying that, I see.
Essentially, if you start off at A, and then go down to B, and then from B, go to D.
It's not like the direction in which you go through the letters makes a difference.
Right.
It's still just an angle.
Right, exactly. And then supplementary angles are two angles that add up to 180 degrees. You might notice here that we don't have three letters. That's because at Q you only have one angle taking place, from blue to green. Similarly, at R you only have one angle taking place. So you could just say angle Q, and there's no confusion, there's no ambiguity. Plus angle R, again, no ambiguity, because only one angle is happening at the point R, equals 180 degrees. Is that clear?
Yes. And they're saying that angles Q and R are supplementary.
Exactly. Now, the reason this comes in handy is for line-line intersection. And some of you might now go, oh God, no, because you might remember this from school. Don't worry, it's really, really simple. When you have two lines that intersect, you might not know anything about angles A, or the angle at A, the angle at D, and so on. But you do happen to know that since the green line is a straight line, the angle A plus the angle at D have to be supplementary, because a straight line essentially has a straight angle in it.
And that's a supplementary angle.
Right, and supplementary means 180 degrees. Similarly, angle A plus angle B equals 180 degrees. But if you remember from earlier when we were talking about the different properties of equality, this would mean that angle D equals angle B. If you can think back, I think it was even the first Math VTM lesson. Because the concept here is that you know that if you're moving along the green line, you got 180 degrees. It's a straight angle. If you're moving along the blue line, you got 180 degrees. It's a straight angle. But that would mean that the angle at D and the angle at B, both when at either, if you add either D or B to A, you'll get 180 degrees. And then by equality properties, that means D equals B, or angle D equals angle B.
So it will allow you to find angles. If you have certain angles, you can use these properties to derive other angles that you may not know the exact value to.
Exactly. So knowing, let's say, only angle A, now you can find out stuff about B and D. Similarly, you might realize that, wait, angle C plus angle B equals 180 degrees. And knowing this, you now know that, wait, angle C must be equal to angle A. So essentially, knowing only one of the four angles in this drawing, you can find out all the other ones. AB and AD are both supplementary. And then A and C are equal. And knowing that, it's very easy. And another way of thinking about it is that opposite angles, like that are across from each other, across from each other, are equal, whereas adjacent angles, like A and B, are supplementary.
I see. So right off the bat, if you happen to know C, then you also know A.
And if you know C, you also know B and D.
Right, because then you can just figure out what finishes 180 to make the
right,
straight line.
So like 180 minus C
angle
equals B and D. Excellent. So now we're going to do the transversals with parallel lines. A transversal is essentially a line that intersects with other lines. In the case of parallel lines, however, see, the green line crosses both the two parallel lines, the two blue parallel lines, then you have a whole bunch of things in common. Well, let's say we only knew angle A. Give me an angle for A.
So let's say A is, I don't know, how even you want it to line up. Say it's like, I don't know, 60 degrees or...
Okay, 60 degrees is good. I can work with 60 degrees.
Okay.
60 degrees. Well, then immediately you know that angle C is also 60 degrees. And this is getting really hard to do with my hands, so I'm going to try, everyone gasp, to use the tablet.
Alright, everyone prepare for a transition?
Now! Okay, let's see here. So now we know A and C. We also know that angle B is 180 minus 60, which, correct me if I'm wrong, is 120.
Sounds right.
And therefore, angle D is also 120. So suddenly, knowing only A, we figured out all of the other ones.
B, D, and C, or B, C, and D.
On the same line. But now, can we determine anything about these angles on the other line?
I would say yes, since the slopes are the same, therefore the angles must relate to one another.
Exactly. Since the E, F, H, and G correspond to angles A, B, D, and C, you can extrapolate from that. Well, the first thing you know, well, you should know, you might realize, is that corresponding angles. Corresponding. That's an I. Corresponding angles are equal. So if you take angle A, its corresponding angle on the parallel line would be E. So A and E are equal. So therefore you know that E is 60. And B and F are equal. D and H are equal, and C and G are equal. Because, like Logan said, the lines are parallel, the angles correspond directly. Corresponding angles are equal. Another property that might help is that, I'll write it down here, alternating angles. There's a property for those. An alternating angle is essentially, if you draw an imaginary Z, or backward Z, between the two parallel lines, the angle that takes place here is going to be equal to the angle that takes place here. So, not only are A and E equal, but C and E are also equal. So, I don't know, find somewhere to write. Angle C equals angle E. And if you drew, I'm going to change it in color before this gets really confusing quickly. In color to green. Actually, green's a bad choice. Logan, give me an in color.
I don't know. You could do blue. Blue would stand out.
I'm just saying the lines are blue. Maybe yellow.
Yeah, yellow would be too bright. Maybe.
Everyone's like, just pick a damn color.
Then grab black.
Black? Excellent. Black has been chosen. So if you draw another alternate angle, Z, you know that D equals F. And I'll just write up here for corresponding that, let's say, angle A equals angle E. And it's getting really cluttered on the page right now, but don't worry, there's only one thing left. And it's really simple. If you take alternate angle, not alternate, interior angles on the same side of the transversal. So essentially you went like this and drew a C or a backward C. And you got these two angles, C and F, that are interior, they're on the inside, and they're on the same side of the transversal. So in this case, they're on the right of the transversal. Then they're supplementary. So, interior angles, so angle C plus angle F are supplementary, so they're 180 degrees. And knowing just these three properties, and there's a handful of others that I'm not going to bore you with, because these three are more than sufficient, knowing only one angle on either of the two parallel lines, so knowing A, B, C, D, E, F, G, or H, you can suddenly determine all the other angles.
Because they're all either going to be corresponding corresponding alternate or interior.
Exactly. Or they're going to be opposite if they're on the same line, or supplementary if they're on the same line.
Right.
And knowing only these three properties, you can determine all of them. So if this confused you, because we jumped between inks and we fought, feel free to watch the slide maybe again, just to make it clearer. And now we're at the end of this lesson. So all you have to do is try to solve these problems. So in part A, try to convert the following lines from the form written into at least one other form. Probably all of them, or at least most of them, can be converted to all the other forms, or at least most of the other forms, but only try to convert to one. And in fact, don't always pick the same one. I showed you 4 different forms, so try to convert each of these into one of those 4 forms. And secondly, solve for the point of intersection of the following pairs of lines. Now, we didn't really talk about this very much, how to solve for it. But in fact, you already know how. In the previous lesson, we talked about, actually the previous 2 lessons, in both of them, we talked about solving systems of linear equations. Well, if you're trying to solve for the point of intersection of 2 lines, just say that the lines are equal, and then solve for what the point of intersection by saying they're equal. Alternatively, if you can't figure out how to do that, just set them up as systems of linear equations and use, let's say, matrices or any other method that we talked about to say, hey, if they're intersect at that point, they'd have in common. And suddenly you can solve it using systems of linear equations. And with that wraps up this lesson.
Cool. I'd like to thank Rob for taking the time to walk us through all these examples and concepts. And I'd like to thank all of you out there for following along with us.
Exactly.
So,
Thanks a lot, guys.